Hey guys, can you hear me okay?
Yeah.
Great, thanks. Let's see what was I doing here. All right, let's see. All right, okay. Hey guys, can I get your opinion about something I'm thinking about doing for next semester? I was wondering what you guys might think of it. So what I was thinking was to basically record the lectures or whatever it is. Just the lectures are all recorded. Okay. And then they would be up on YouTube. The whole semester would be up on YouTube. And I guess, you'd go on, at your own, whenever you like, before the class, watch the lecture video. And so the lecture time would be so just be live or in person. I don't know what's going to happen next semester. And it'll just be, answering questions. It would be, delving into deeper into some parts of the lecture. There's questions about sort of, if there's something doesn't make sense in the lecture, to go over it in some other words or in some other way to try to convey the information, and or do problems, do work on a project together, that kind of thing. What do you guys think of that? Any thoughts?
And if you don't want to hear our beautiful voices next
Yeah.
semester, Professor, I think it would be a great idea.
Yeah. No, I mean, you would still be, so they would still have the live sessions twice a week, but it would just be the lectures would be recorded, and those live sessions we could talk and sort of get into details in more depth. I'm just thinking like for me, the lectures are essentially constantly the same, um, for me. And I don't, during the lecture anyway, I don't get like a huge number of questions, whether from you guys or the other class I'm teaching. Um, so it would be recorded, and then our live session together would be, talking about it or whatever is on your mind.
To be honest, Professor, it sounds pretty good, like a good idea. I think my other elective class, 4200, kind of does that. He'll have like a live lecture every now and then. So
Mhm.
he'll record every single one for about 2 weeks. We meet up twice, just like this class. And on the fourth meeting or like the eighth meeting, or whenever he feels that there's like a lot of people emailing him, he'll open up a live lecture like on the actual time and date. And we could go ahead and hop in there and ask him questions and stuff and go over examples.
Okay. Okay. That's a cool idea. Any other input? Anybody else seen other formats? If it has to be an incentive to watch the video. Learning, man. Come on, Salvador.
Yeah, it seems like a good idea.
Yeah. Yeah, just because I mean, for me, I hate to say this, but for me, I'm like semester after semester, I'm like sort of repeating the same stuff in the lectures. So recording them seems to make sense to me. And then the stuff that I feel like we aren't getting enough of is the interaction and like digging into different parts, maybe doing problems, maybe looking at actual design problems, those kind of things. And I'd rather do that live a couple of times a week than just sort of being giving you guys a monologue. So anyway, thought I'd get your input before I make the next semester of people suffer. Okay, so let's see, where were we? Oh, and I think you guys, was it Logan? I forgot, maybe a few of you guys were asking about the schedule
Midterm.
for the midterm
Yeah.
2.
Yeah, the syllabus says that it was scheduled for, I believe, Thursday.
This coming Thursday?
I believe so. It's week 14,
Ew.
right?
Is it? I have a tendency to lose track of time. So it won't be this Thursday. I think that would be bad behavior.
Woo!
Yay. So when is this semester over anyway? For some reason, I thought it was in first week of June, but
I think finals are anytime between like the 15th and the 18th or something like that. It's around the 15th
of May or June.
of May. May.
Yeah, finals week is the 17th through the 21st.
Yeah, like 3
Okay.
weeks.
Jesus. Yikes. Okay, well,
So we're just gonna have a final then instead of the midterm.
yeah. What do you guys want to do?
Project. I'm just kidding.
Huh?
It probably, I know there's some professors that try to squeeze those midterms right next to the finals, but kind of seems pointless sometimes.
Yeah. So we've had how many? We've had 3 projects or 2 projects so far?
We've had 2.
2. Hmm. Hmm. How about I just give you guys a gnarly project? I mean, use that as the midterm too.
Final.
What do you
Or
guys
as the
think of
midterm?
that? What's that?
Define gnarly.
Define gnarly? It's just a
Yeah.
little more difficult than the previous projects.
That's gonna be fun.
Hmm.
So like as a replacement for the midterm, is that what you're saying?
Yeah, yeah. Because I mean, I actually like. I think. What do you guys think? I feel like you probably learn more in the projects than you do studying for the tests for this class, anyway.
Yeah.
So I'd rather have you guys do that than. I mean, personally, honestly, if I was gonna, if I actually, I don't know if I have my hands tied. I was actually thinking of not having any tests this
Whoa.
semester and just have projects. But anyway, it's what do you call it? Wiser heads talked me out of it.
So you're saying that we have a project that supplements the final too, huh?
What's
Oh,
that?
project equals final?
Yeah, there we go.
Like
'Cause I mean,
gnarly
this class,
project.
yeah, this class has 2 midterms and projects. So we could just basically blow off.
Oh, there's no final in this course?
No, there's no final in this course.
Oh, I'm thinking of the wrong one.
Syllabus is all
Yeah.
midterm projects.
Got you. Okay, yeah, I'm fine with a project.
Yeah. So anybody object? Going once, going twice?
No.
No? Yeah, I mean, I think, what's that? What's that, Joseph?
Project sounds good.
Yeah. Yeah, we can make the project due. When would you guys like it due? So we could.
Probably
make
like the
it
final
due-
week.
Yeah, we can make it due end of the final week. I don't really care. I can just
Yeah.
grade you guys. You guys said finals week is 17th through 21st, so we could make it due on the 21st or something.
That works.
That's
Yeah.
good with me.
Okay. So I will, it's gnarly, but it's, whatever. It's not too bad. Ha. So you guys, I think it's better than, I don't know, studying for this class. I don't know. It just doesn't, to me, it's not like a test kind of class. It's more like, I think projects make sense.
Oh, this course is electric course, I think. Just yeah.
What's that, Minjin?
I mean, this car is electric cars. I think just like
Yeah, makes sense too from that point of view. Okay, guys, sounds good. So we'll just blow off the midterm 2, and I'll put up a project. I'll put it up for Thursday. We can go talk about it a little bit, and then it'll be due on the 21st. And so, okay, it's a deal.
Just to clarify, so you're gonna post the project 3 this coming Thursday, right? And then it's gonna be due like the final week,
Yeah, it'll be due at the end of the finals week. So you'll
Okay.
have
like 3 weeks to do it.
yeah, it'd have like 3 weeks to do it.
Alright.
Yeah.
Professor,
Okay. Yeah.
I was just wondering, have you submitted any of the grades for the mid that we did?
Nah, sorry. I got like almost finished it, and then I got sucked into some other stuff. I'll get it done this week. Sorry, guys.
Okay, no worries. I was just wondering.
Sorry about that. Any other questions, guys?
All good.
All good.
Okay, cool. All right, guys. So let's. So this is my most. I think this is like the most difficult subject for me and for lecturing, because it's like kind of complicated to explain what they're trying to do. So I think hopefully the stuff we were doing up to this point of looking at the delay of individual stages made sense. And so the next step we're taking is trying to come up for the entire delay of a multi-stage network, which is, again, something it's much more likely that you'll be faced with a multi-stage network than a single stage network. This is logic has usually got a bunch of networks. It's a bunch of layers. And so the idea, again, I want to emphasize this over and over and over again. The idea here is that this is not to be instead of the computer simulations, whether it's SPICE, whether it's something else, but this is something you do at the beginning of the project to make sure you're on the right track, make sure you're using the right process. So these are all kind of, approximations, but also I think they give you some interesting results. The problem with, especially as soon as you end up having, let's say even in this case, like we're talking about, I don't know, 4 devices, right? You have 4 of these guys. Imagine if you had this, an inverter, you don't know the sizes, you have an inverter, 2 input NOR gate, 2 input NAND gate, another inverter. And you're driving the next stage. So you say the load. So to optimize the speed of this, to figure out the fastest that your design can go, basically, you could start size these devices a certain way and start, adjusting them up and down. And, if you had a problem of trying to optimize this value, you can just imagine how long that would take, because you have 4 things that you'd be adjusting for. And in fact, as you say, if I'm changing the size of this guy to drive this faster or slower, it's slowing down this stage. As it's getting bigger to drive this thing faster, it's slowing this guy down, etc. So they're all like affecting each other. And I have 4 things I need to change. So to optimize this in a simulation environment, it's, I don't know what you want to call it. It just like you're just moving stuff around, getting values. You don't really get a good feel about what it means or what the parameters are doing. And it's just very time consuming, even in simulation. Although you get accurate values, you're not sure if you're completely optimizing it. So this is what this idea of logical effort is trying to sort of come up with a estimation method to help you optimize it. And the idea is that it's coming up with a, you know, we saw the logical effort for a single device. So for a single device, single logic gate, we had logical efforts was small g, and that was, you know, 1 for an inverter. And my handwriting did not improve much. Inverter, it was, you know, maybe remembering these wrong, but 4/3 for a 2 input NAND. I think it was 5/3 for a 2 input NOR, etc. So that was for a single logic device. So we're saying if you have multiple logic devices in series, call the path logical effort the multiplication of all those values. So you'd have, this would be 1, 5/3, 4/3, and 1. So say capital G for this path would be all these values multiplied by each other. Whatever that is, it's 20/3. So that ends up being your path logical effort. And we had the individual, so single stage electrical effort. And that was whatever C out we were driving compared to our own input capacitance. So H was C out over C in. And the path electrical effort is the same, except it's looking at just the output compared to the input. So how does that work? So it's just, by the way, that's just H. So here in this case, it would be 20/10 or 2. And the usual idea is that if you are given a block to design or optimize, typically your output goes into another block. Let's say it's being designed by somebody else, or in any way, what you do with designs is that you partition them. So let's say you've partitioned this and you're optimizing this value, then you have the next stage that this is feeding into. So you have to come up with some decision about what the loading of that next stage is going to be. So that's either by agreement with other people in the design team or with yourself, knowing that you've got this other block to do. You go, okay, well, this is the budget I have for driving a certain amount of capacitance at this output. And presumably the same thing has happened. Something else is driving the input for this block you're optimizing, and that's telling you, well, the most I'm permitting you to size this thing is, you know, just give it a 10 times the, actually, I guess it would be 3 times the size of a unit inverter. Okay, so in this case, it's this ratio from just the output to the input is 2. Notice I haven't talked about any values in between here so far. So I haven't, all I know is I know the size of this guy because that gives me the input value, the permissible input value. I know what I'm driving, and then I know the functionality. So by knowing the functionality, which told me the logic gates I'm going to use, so not just the functionality, but this particular implementation of the functionality, because presumably, like, you know, I could change these with some, you know, I could, in a general sense, I could replace those with another type of logic gate or another set of logic gates to get the same functional output. But for this particular implementation of the gates, I haven't picked the sizes yet, but I've said, okay, this is the particular implementation I want to do to get this particular function. Okay, so having said that, I'm going to define this path effort to be the multiplication of all the G's and H's. Okay, so so F would be, I don't know, and I don't know what the H's are. Okay, so I'm going to keep that variable. So imagine this F, capital F, is all these guys multiplied by each other. Okay, so right now I'm just defining this, and I'm going to use this to come up with an optimal value for the delay per stage. Okay, so right now I'm just defining stuff. And then we said that because in a multi-stage network, we're just drawing this like this, but there's a possibility there are other branches in this logic. We somehow have to account for those as well, because if I have, it's not enough to get this, for example, 20/10, but there might be other branches here that are slowing, that are weighing down this speed, and I have to add those. I have to consider these to help show that the speed isn't going to be that fast. It's going to be reduced by these other external loads. That ends up being this branching effort, which is divided. Every time we get a branch, we basically get a ratio of what's in signal to what is total, and we use that to basically effectively increase our electrical effort. So our capital F, our path effort, increases by the number of branches we have on the value of those branches. Okay, and we tried to show that needs to be done. Okay, and so in the end we came up with this value for the overall path effort. Okay, so that's where we started from, and now we're going to try to use this to help come up with an equation for an optimal electrical effort per stage. And the way we do that is we go back to our original definitions of effort delay. Okay, so the total delay is, so I'm stopping here, so hold this thought. This is our definitions, etc., that we came up. So this is the total path effort to drive something that the G represents the implementation of a certain functionality. So remember, this was basically this represents the types of gates you're using all multiplied together, without any sizing information. B is the branching effort. It talks about stuff that's off of your main signal path that you're trying to optimize. It's still loading your signal path. And then H is a ratio of the final load you're driving compared to the very initial input load. So this is this effort delay that we've defined, and we want to figure out how to optimize this value. We want to figure out what's the minimum value for this thing, for this path that we've come up. So if we have this functionality, so this particular implementation, this particular load, and this particular input, what's the fastest this can operate in? Okay, so you need to optimize capital F to do that, the path effort. And using that, we'll want to also figure out how to size these guys exactly to get that fastest speed. Okay, so that's what we're trying to do. And this is without knowing, without having to tweak each one of these individually to try to come up with an optimal value. We're trying to find a systematic way of doing it. Okay, so we said that's our definition of effort, path effort. Okay, So now let's think about the path delay. If you look at it as individual elements. So again, the path effort was looking at the whole path because, for example, it was looking at just the last stages, the loading where we're driving on the last stage compared to input of our stage, etc. But if you just look at each individual stage independently, okay, we would say that, you know, the total delay is the sum of all the efforts. So it would be, for example, in this case, it would be, so D sub F would be, I don't know, G1, H1 plus G2, H2 plus G3, H3 plus G4, H4. This is, let's say, in the case of our we had 4 stages here. So it would just be basically the sum of all those delays. That would be our path effort delay. And the path parasitic delay is just the parasitic of all those summed up. So it'd be, you know, P1 plus P2 plus P3 plus P4. Now remember, we don't know these. We know G1, G2, G3, but we don't know the H's, the individual H's at this point. Okay, so that's kind of what we want to figure out. So that's our total delay. Okay, so this is sort of the real difficult part to explain. So what we want to do is, let's just look at the forget about the parasitic delay for a second. So I'm going to not focus on this. So I'm just going to look at the effort delay. So there's D sub F. Okay, now I want to say, okay, so I want to make, this is the sum of the delays of each stage if I knew H's, individual H's, which I don't. Okay, well, that would be the sum of them. Okay, and F is the product of the stage efforts. So this I know, because I know the G's and C out and C in. Okay, so I know this one. Okay, so this is G1, H1 plus G2, H2 plus G3, H3. This is G1, H1 times G2, H2 times G3, H3, da 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 da. Okay, everybody with me so far? Any questions? So I'm just laying down the math here. Okay, and so the main thing is that there's this math, I don't know what you call it, hypothesis, theory, whatever you want to call it, but that the sum of a set of numbers okay, so this is D sub F. So this is, in this case, right? This is just a mathematical statement. I'm saying, like, in this case, think about the sum. So this is some set of numbers. D sub F is minimized by choosing, oops. All numbers to be equal. Okay, so these numbers. Okay, so we've got this mathematical statement that if we want to minimize d sub f, which is a sum of a bunch of numbers, is a sum of a bunch the delays. Okay, so if we want to minimize this, we want to make each one of these stages, so the multiplication of all these things, you want to make all of these guys individual ones the same. That would minimize d sub f. Any question about that? Does that make sense? So in other words, we want to make all the g sub h's, okay, the same. So we want to make g1 h1 is equal to g2 h2 is equal to g3 h3 is equal to da 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 da. And so this would equal to g times h to the nth power, whatever number of stages you have, is equal to f. Okay, because they're all the same. So in this case, we are saying that we want to make g1 h1 is equal to g2 h2 is equal to g3 h3 is equal to g4 h4. We're saying if we do this, the sum of all these numbers, which is giving the delay, the total delay from here to here, is going to get minimized if we do this. Okay, now, and that this f is g1 h1 times g2 h2 times g3 h3. So if these are all the same and I just call them g times h, so g1 h1 equals g2 h2 is equal to g times h, this would be f is equal to g times h to the fourth. Okay, and then g sub h is equal to f to the 1/4 in this case. Okay, I have the f in this case, right? Because it's just the individual g's and the h for the path. So I have that. And what I'm saying is, if I make each one of these guys that path effort delay to the power of a fourth, I can calculate the h's and make sure that I have, for this implementation, I have the minimum delay. And that's what this equation says. It says you want to make all the g times h's the same, and that will mean that given a certain number of stages, n, basically each one of these will be f to the 1/n. And then you'll end up with a minimum delay. So d, the minimum delay, minimum d, is n times f to the 1/n plus p. So this guy is d sub f. Okay, I'm sure you guys are confused. I'm confused. Okay, do you guys want to try? Let's do a example. Okay. Any questions, by the way? Oh, scroll up a bit. Sorry. Here. Salvador? Okay. Let me know when you're done. Okay, great. Okay, so let's do an example. Okay, so we have, okay, so let's say, what is this trying to say? Let's say you had, it says you had some function that you're trying to create in logic, and your implementation gave you these gates. Now, again, the reason I keep saying the particular implementation, that's because, you know, maybe you could have implemented this instead of with a 3-input NAND gate, you could have done some other implementation, you know, maybe the 2-input, I don't know what it would be, a 2-input NAND gate, maybe 3 2-input NAND gates, I don't know, but, you know, whatever. So you could have done some other implementation that would have given you a different number of layers. But let's say you pick this, okay, and you want to analyze it. And then let's say you had a few other paths, right? So each one of these things, just, they don't have to be equal, but just to make it simple, these other paths, the loading is equal to the same gate that's loading down the primary path you're interested in. So we want to figure out what is the minimum delay from A to B, and we want to figure out how to size this X and Y gates. Okay, so that's an example of how this could get used. Okay, so first thing we're going to do is come up with the logical effort, okay, which is G. So this is, do it, capital G. Okay, so first thing you got to come up with, so remember this is G1 times G2 times G3. So this is going back up, where were we? It's this guy, path logical effort. Okay, so it's the multiplication of all these G's. So we got to come up with the G's. Okay, so all we have to do is to go to the table somewhere out here. Okay, this gives us the G's. So we have a 2-input NAND. So that's a 4/3 G. We have a 3-input NAND, which is a 5/3 G, and a 2-input NOR, which is a 5/3 G. So I'm gonna just write these all down here so we won't forget. Where is it? There we go. So this G is 4/3. This G is, let's call this G1. Let's call this G2, 5/3, and call this G3, 5/3. Okay, so this one is 4/3 times 5/3 times 5/3, which is 100 over 27. Okay, the electrical effort is H, and that's basically the ratio between what I'm driving at the output compared to my own input. So that's 45 divided by 8. Okay, branching effort is the ratio of, so branching effort, where are we? Is the total capacitance divided by the on-path capacitance. So basically, this is the kind of you don't have to do the same device, but it helped us to do the same device. So the total capacitance is, let's say the capacitance of a 3-input NAND gate was X. Okay, so we just define that as X. Okay, so the total on, so C total for this stage is 3X, and then the on path is equal to just one of them. So 1X. So this would be 3 for the this branching effort. And then we got this branching effort. So let's call this B2. And for this one, let's say, the capacitance of 2-input NOR is 2. So I have 2 of those guys total. So I got 2Y. And then my on path is just Y. So that ends up being 1Y. So it's 2. So this is 3 times 2, 6. Anybody have any questions about how you got that far? Okay, so then the path effort is capital G times B times H. So it's 100 over 27 times 45 over 8 times 6. Okay, so that's 125. Okay, so now here comes the magic of this thing. We're saying that because of this consideration, again, the fact that the sum of a set of numbers is minimized by choosing all the numbers to be equal, basically our best stage effort, or this is the stage effort, so this is the optimized stage effort per stage is this F we just calculated at 125 to the power of 1 over n. The number of stages is 3, right? We have 1, 2, 3 stages. So the best stage effort, which is kind of F hat, which is, the best G times H, G times H, the optimized G sub H is 125 to the power of 1/3, which is 5. Okay, everybody with me? So if I made this G times H for each one of these 5, I would have an optimal delay. I still don't know what that optimal delay is, but it would be the optimal delay. Okay, so let's keep soldiering on here. Now we still need the parasitic delay. All this stuff so far has been the effort delay. So now we need to figure out the parasitics. Okay, so that's total. So the P, again, to figure out the parasitics, I just go to the parasitics table. The nice thing is once you've done this once you got these tables, you don't need to do it again. So I've got my parasitic delay. So again, I had a 2-input NAND, so that's parasitic delay of 2. I have a 3-input NAND, 3 parasitic delay, and 2-input NOR, I got a 2 parasitic delay. So let's write all that stuff down. Where are we? Yep. So P is 2, 2 this P is, so P1, P2 is 3, and P3 is 2. So P is P1 plus P2 plus P3 is 2 plus 3 plus 2, and that is 7. Okay, now here we go with delay. So the delay is, so this is the optimal delay, is this guy. Okay, so it is okay, so the number of n was 3, because this is my particular implementation. So I did it with 3 stages. So I have 3. F to the 1 over n is my best stage effort here. So that's 5. And then P is 7. So I have 22 is my, so this is the fastest delay that I can achieve. Now, let's say I want to figure out, hey, what's my delay in a 65 nanometer process? Well, depends on the 65 nanometer process, but we've been using an example where the tau was 3 picoseconds. Remember, tau is 3 RC, and the R and the C, we sort of depends on the transistor parameters for that particular process. Okay, so if I am in this particular 65 nanometer process, the optimal delay of this situation is 22 times 3 picoseconds, or 66 picoseconds. And, you know, if I had a 0.18 micron process, I would end up with a different tau. It'd be larger than this tau, maybe probably by a factor of 5 or something, 3 to 5, whatever. And it would give me a different delay for this particular implementation. Okay, so with this approach, I'm saying this is the best I'm going to do for, you know, this is a sort of a process independent number, and, or maybe I should just call it tau. No, I'm not going to add the tau, because that's, so the actual delay, actual delay is d times tau. And tau was, you know, process dependent. Okay, and this is again for a 65 nanometer process. Okay, so with this, we're saying this is as good as you're going to do. Okay, which is already like an interesting result, because you can say, okay, well, I want to implement this particular logic in this way. I haven't gotten to sizing it yet, but I can already tell with this particular implementation, this is the best speed I can get from A to B. Okay, it is just 22. Now, again, like usually there's multiple ways to do an implementation. Maybe you could have done more number, maybe you could have done it in 4 layers, but instead of using 3 input gates here, you could have used 2 input gates. So you could also figure out pretty quickly, I mean, once you put this in an Excel sheet or whatever, you can pretty quickly come up what's the delay of that. And it might be more or less than this delay. Because remember, a 3 input NAND gate is slowish compared to a 2 input NAND gate or an inverter. So if you replace it with something else, maybe even 2 layers, replace this with 2 layers, you might actually end up doing better. You don't know. because, you know, again, the more inputs a gate has, and the slower it is. And if you use NANDs instead of NORs, they tend to be also faster. So you could do a bunch of like if-then analysis and figure out what's your optimal delay. And again, you can do this all in, you know, an Excel sheet format, whatever. And the book has an example that I have in the slides, but I'm probably, you know, it's going to get too detailed to go through. So, okay, so that's already an interesting thing where you can find an optimal delay through your path. Okay, the next thing you can do is you can work backwards and actually get the sizes of your devices, okay? Because we know what the effort delay, so we know what this F hat is for every stage. So we know the F hat for each one of these stages is 5. We know what the G is for each stage. So for example, G here is 5/3. G here is 5/3. So G2, G3 is 4/3. So from this, we can figure out what the optimal, so we go basically start from here and we go work backwards. We come over the optimal size of this. This is the loading for this, and we come up with the loading of that. The reason is we've got G3 times H3 is F hat. Same with this. G2 times H2 is F hat. And G1 times H1 is also F hat. Okay, so let's work backwards. So let me actually write this equation down because it always helps me think. So this is what, so for each stage, so this is G, C out over Cn as H. Okay, so we're saying G times H in each stage is F hat. Okay, so C in at each stage is this value, working backwards. Okay, so let's look at this. So what do we got? We got, as the first stage, we have so G times H is equal to 5. Okay, H, so this is for this stage. So for Y, we have G is 5/3. H is 45 over Y. So we want to figure out Y, this size. So we know the output size. We want to figure out this size. So this is H, with Y as being the unknown. And this is equal to 5. Okay, so I end up with a Y is equal to, this is, cancel each other out, Y is equal to, that's right. So, wait a minute, Y is basically 45 divided by 3 is 15. Okay. So the total loading here on this input should be 15. Okay. So what does that look like? Well, let's implement this guy. So this guy looks like a 2-input NOR gate looks like this. And so let's say these are X size. we know to make the, so this and this are X wide. I shouldn't use X because we're using X for something else. Let's call it, I don't know, B wide. So we know to make the, the pull down, same resistance as the pull up, because these two are in series. If these guys are B wide, these guys better be 4B wide. Okay, and these inputs are connected together. So this basically says that 4B plus B is equal to 15. Or B is equal to 3. In other words, to size this guy optimally, we would have to make these guys 12s. No, yeah. And then these guys 3. Meaning 3 times the unity inverter gate and inverter size. Okay, so now we've got the sizing for this NOR gate that would give us the optimal delay. Okay, now we have this loading. This is the C out for this stage. So now we can use the C out, which is now this is either C in for this stage or the C out for this stage. So now we can use that to figure out the input loading of this stage. So we do the same thing. So for G times H here is also equal to 5. G is 5/3. H is 15 over X is equal to 5. I did this right. X. I screwed this up. Haha. I screwed it up because I didn't include the delay. So C out is not just this, but is this plus that. So beware. See guys what I've screwed up? So I just called it, the C out is just 15. It's 15 plus 15. Okay, so this is wrong. So it's 15 plus 15 over X is equal to 5. Okay, so X is equal to 10. So you guys see that? We figured out this is the input capacitance of Y, but for this guy, it's driving 2 Ys. So if I'm trying to figure out its H, I got to include both of those guys in my output capacitance. So I end up with the X of 10. And in this case, I'm going to go to a separate page. And so if I was going to draw this gate, it would be, it's got 3 P MOSFETs and 3 pull downs. And again, I know to make the pull down the same as the pull up, I need to make this 3 times, let's call it C, I guess. No, C is another bad one. 3A, let's call it 3A, 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 and this is 2A, 2A, 2A. You guys see what I'm doing? I'm just saying this, if I'm trying to figure out what A is, but I know how I need to ratio the pull down with the pull up to equalize the resistances. And because these are inputted together, I basically get 5A is equal to my input, which is X, which is X. So A is 2. So basically what I would end up with is six, 2, 2, 2. So now, not only do I know this is the optimal delay, okay, 22 tau or 66 picosecond for our example 65 nanometer process, but I can also size these devices to give me that optimal delay, okay? Which is, this is like pretty key because, again, I didn't need to start playing around with these sizes. I guess this was set, I guess, by the maximum size that I could make this. And this was set by what I was driving. But I chose this configuration, and without having to play with these guys again, but I had a bunch of orders, a bunch of degrees of freedom, which would have given me, I've been simulating this forever. And I couldn't prove that it's the optimal delay, but now I can show what the optimal delay is and what the how to size these devices. Okay, which is kind of a really nice function. Okay, so I'm gonna come back, but this is like this example. I'm not gonna go through this example. It's worthwhile going through the book. The reason it's just a bunch of like if-then analysis. It's this example of having to design a decoder we talked about at the beginning of the lecture, which is, has these inputs, the decoder. So the idea behind the decoder is by, giving it a 4-bit address, I get one of these outputs goes high. Okay, and I have a certain loading for this thing and a certain maximum input. So I want to figure out what's the fastest I can make my decoder. Okay, and these are the, how many stages, how large, how fast it can operate. And, again, this goes through a series of if-then analysis, and he ends up with a table because there's more than one way to get a decoder. You can either make it a single stage with, 4-input NOR. You could do 4-input NANDs with inverters. You could invert first to buffer the NAND to invert it, and so on and so forth. You could basically come up with a bunch of different implementations of a decoder, okay? And then using that, each one gives you a different number of stages, and each one gives you a different G and P, and you can get a total delay, okay? And it turns out, interestingly enough, that, the lowest, this is the lowest delay. If again, I got to follow this example, and he's using, you can use this in an Excel sheet or whatever. The lowest delay, the optimal delay, ends up being not just a single stage, but like 4 stages, but with each item in the 4 stage having a lower number of inputs. So it's using NAND 2s and inverters. So it's using NANDs, which we know are relatively fast, and it's using 2-input NANDs, which we know are faster than larger number of input NANDs. And that ends up being the lowest delay, which is interesting. You might think, well, a single stage NAND inverter, I guess this was where I would have gone, would give the lowest delay. And it turns out not to be the case. Okay. Not sure if this is the right number here, is it? And maybe it is. Yeah, it is. That's just a horrendous. Is that right? 1 G. Jesus Christ. Wow. It's amazing. I mean, look at this. This is really hard to believe, but I guess the numbers worked out. If you decided to do this with NOR 4s, your decoder, look at the delay you'd end up with. Wow. It's like amazing. Hard to believe. But anyway, that's an interesting thing. You can basically do this pretty quickly and compare your different alternatives of implementations for the decoder. Okay. Again, I think you guys might want to, this is in the book, and again, it's a bunch of if-then analysis, so it's hard to do during the lecture. Let's see, what else did I want to do? Okay, so we did this example. Now, let's look at another example. This is also something that you come across pretty often, and that is you're trying to drive a big capacitive load. Let's say you're trying to drive a load that's 64 whatever times bigger than, or like 64 divided by 3 bigger than a unit inverter. And the question is, how do I drive that load? What's the fastest way I can drive this guy? Do I use a single stage? So this is an inverting buffer. This ends up being a non-inverting buffer, inverting buffer, non-inverting buffer. Usually it doesn't matter if you use an inverting buffer or non-inverting buffer, because you can always kind of invert later. So a lot of times people don't think of it as being particularly important whether to use inverting or non-inverting buffers. But like, so this would be non-inverting, this would be inverting, but for all events and purposes are sort of similar. So the question is, which one of these is the fastest approach? Do you use a single stage and make it really big? Or do you use multiple stages and try to stage them? Okay, so let's take a look at it. So the capital G here ends up being 1 because we're all using all inverters, no matter what, they're all 1s, right? So they're going to multiply to be a 1. Okay, now capital H is 64 because the first stage is always 1 size and the output is always 64. So H is 64. Okay, and the parasitics are going to be different because the parasitics are going to sum up in value. So the parasitics are going to be a little bit different. Okay, so let's look through this. So D is going to be n times square root of 64 times n plus parasitics. Okay, so let's look at these different cases. Okay, let's say in this case, n is 1 because I'm driving it with a single stage. F is going to be F is going to be this guy, right? So it's going to be 64 square root of 1, so it's just going to be 64. Okay, so F is just, oops, 64. So D is going to be 1 times 64. So I only have 1 inverter, so my parasitic is going to be 1. So this delay is going to be 65. Okay, so that's this guy. This guy has 2 stages. Okay, the F is square root of So let me just, instead of doing square root 2, I'll just do 64 to the 1/2. So is equal to 8. Okay, P is 1 plus 1 because I got 2 inverters, so that's 2. So the total delay here is going to be, it's going to be, I've got 2 stages times 8 plus 2. So this is going to be 18. So notice this implementation with 2 inverters is, I don't know, almost a factor of 4 faster than with just 1 inverter driving it. So this is significantly faster than this, which is, this is the kind of the important result is a lot of time when you have big loads to drive, you want to basically stage up your size of your buffers and drive it with multiple buffers. It's a lot of times faster than just doing a single stage. Okay, and I can keep doing this. This is 3 layers deep, and it's 64 to the 1/3 is the F, which is what is that? I think it's 4. The P, I have 3 inverters. So so D is going to be 3 times 4 plus 3. So this ends up being 15. So you can also see that 3 stages is better than 2 stages is better than 1 stage in terms of the total delay driving that load. And then finally, I have 4 stages, 64 to the 1/4. That is 2.8. And P is equal to 4. So D ends up being 4 times 2.8 plus 4, and this ends up being 15.3. So the optimal point seems to be kind of around here, because this 4 stages is slightly more delay. 4 stages is slightly more delay than 3 stages. Okay, but 3 stages seems like something like that is the sweet spot. So again, the important thing here to show is that a lot of times the optimal implementation, the fastest implementation is, multiple stages and fewer number of input gates and faster gates. Okay. Now, there's some derivations here of optimizing this thing, but the main thing is that, let's say this is something, a rule of thumb that all chip designers know or think they know, whatever, is if you have a big load to drive, you want to basically size your buffers. The optimal value is that this ratio of sizing is 2.4 to 6x. So if this is a 1x, you want to make this 2.4x to 6x. You want to make this 2.4 times 2.4, this, you want to make this guy 2.4 to 6x bigger than this, etc. And that's the ratio you want to do. So used to be, people used to think the ratio should have been pi. There's this old book that came up with this ratio, which is 3.14 was this golden ratio, would give you the best case. Ends up not being the case, but it doesn't matter. So you want to increase the size of your buffer stages to drive big capacitive loads, and you want to increase that size by somewhere around 3x. I always use 3x. Don't know why. It's just stuck. But there's some derivation in the book that shows between these ratios, between 2.4x and 6x, it's, you know, that this delay curve is fairly flat. So it doesn't really matter what you do. It's between those numbers. So don't ratio up by a factor of 10, and don't just make everything kind of more or less the same size. And, you know, the difference is this, I mean, the book says they like 4, I like 3, doesn't really matter. It's kind of flat around here. And then you start having other considerations like, well, the more stages you use, the more power consumption you also burn. So, you know, this might be, you know, might find the absolute fastest point. For example, in this case, you might say, well, in this case, it's the same, but you'd say that this is faster than this. Like it seems like you don't want to use this at all, right? Because it's significantly slower than these other guys. But you might look at this and look at this and go, well, the delays, you know, the delay of this guy is faster than this, but I've got this, you know, extra stage here that's burning up more power. So, hey, maybe I'm like, maybe in terms of power consumption, this would be worse than this. And, you know, I don't need to be the absolute fastest blazing. In this case, I can give up some speed for power, etc. But there's some options that you have. So, but I think the idea is that there's this, you know, you want to ratio up the devices. You want to, if you want to go fast, you want to ratio up the devices by a factor of 3, 4, 5, something like that between layers. Using more layers is sometimes the ratio of devices sometimes faster, a lot of times faster than just using a single layer. And then a lot of times using 2 input or smaller number of input devices and more layers is also faster. So, and you can use basically this test technique to come up with these sizes. So let me see if what else do I want to say? Yeah, I think this is sort of summarizing, this last page summarizes all these rules of thumb, all of which are kind of good. Yeah. Okay, guys, so let's stop here. And then on Thursday, we're going to start talking about wiring delay. Any questions, guys? Okay. If not, I will hang up on you guys and talk to you guys on Thursday. Take care. Bye.
Thank you, Frank. Have a good one.
Thank you. You too.